All right, good morning. It's 9 o'clock, so I say we get this going. Appreciate everybody's time. Certainly, if you have questions or comments, certainly you can type those in and I'll hit those as I can get to them. Won't take too much of your today's time, but if you do have questions, we can address those online here or offline. So I've been with Richard. My name's Tyler Schrader. I've been with Richards for 10 plus years now. I assume most of you recognize our valve lines that are shown below. Richards doesn't make valves, but it is a parent company to Jordan Valve, low flow valve, Steriflo valve, and the other three listed. Gilson Engineering represents us for our control valves and pressure regulators for the territories you guys are in. So control valves, pressure regulators, back pressure regulators, temperature regulators, those inquiries, questions can all be directed to your inside or outside contact at Gilson Engineering. So today we're going to cover CV. CV is probably the most critical thing when it comes to selecting control valves and regulators. So on every part number you build, whether it's a flow meter or a pressure transmitter or a control valve or pressure regulator, in pressure regulator control valve, CV is the toughest to get, but it's also the most crucial. So we'll spend a little bit of time today covering what CV is and what affects it and how it's important. I put these couple sentences on the screen here so you can read them before we got started, so I didn't have to read them to you. But in essence, CV is an orifice size. CV is the amount, it's the size of an opening that allow flow to pass given a differential pressure and flow rate. Make sure you can check one thing here. Okay. Given the flow rate, given the, I need to minimize this. Given the flow rate and differential pressure in the media that's flowing, it's the size of the orifice that allows flow to pass. I'm going to jump back and forth between the slides here, and then we'll get over into the sizing program, but just want to give a little background. So on the left, we have our sliding gate, which is what Jordan is known for. And on the right is our typical globe style pressure regulator. Let's see here. People saying no audio, but okay, we're good. On the right is a typical globe style pressure regulator control valve. So in both cases, there is an orifice that allows media to go through. Steam, it could be water, it could be air, nitrogen, whatever the process fluid is. So the larger the orifice, the more flow that can get through, obviously, which equates to a larger CV. The sliding gate is kind of tougher to see over here with the black and white, but as those slots get properly aligned, it allows the media to go through, just like the globe style. It's a little easier to see in the globe style. Looking inside of a sanitary pressure regulator on the left and control valve on the right, same kind of situation. We have an orifice here with a plug and the seat where the media comes in and out. The control valve here has a slightly smaller plug and seat dimension. Therefore, it's going to allow less flow, less steam, less water through those ports. I pulled this from one of our data sheets just to show you. CV it doesn't have it's not square inches, it's not square centimeters, it doesn't have a unit that goes with it. But this just shows the larger the line size, the larger the CV. So we have 1/2 inch. The max we can get is a 4.4 CV in our products. 2 inches, 30, and so on. When we have a 2-inch product, a control valve pressure regulator, you can always go smaller in CV, right? You can always get a smaller orifice in the larger line sizes. If you have a 2-inch valve, you can't go up, right? There's only so much orifice available in that pipe diameter, in that line size. So just if you're looking at this, you can always go down in CV. You can never go up to pass how much flow you're getting. Now I'm taking a better look at the sliding gate. I want to point out a couple things here. We have our CVs listed on every one of our products that goes out. So this happens to be a CV of 50. I believe this is a 2 or 3 inch cutaway or sliding gate seat set here. Another thing I want to point out is percent open. On the left side of the screen here, you can kind of see where we see a little bit of the back plate here, meaning the valve is not fully open. Obviously, it's not fully closed because you can see the blue beneath it. So pressure regulators control valves are going to control from 0% to 100% and everything in between. The sizing that I'm going to be doing today is going to cover globe style. Oops, let me go back. It's going to cover both globe style control valves and pressure regulators, and also sliding gates. So we'll touch on both of them. The sizing is very similar for both, but there is slightly different calculations to come up with the CV. And then with that, let's hop over to the sizing program. So we have individual websites for our product lines: Jordan valve, Steriflo valve, low flow valve. But I'm just going to hop into Jordan here, and on the front part of our screen on the right side is we have the sizing software. So if we hit learn more here, it's going to give us 3 options. We have the JVCV is what we call it, online version, desktop version if you want to download it, put on an icon on your desktop for if you're going to use it a lot. Then the classic is the old, probably more outdated one, but I always use the online. It's always updated with the newest formulas and updates. Then we hit Jordan here. We could hit any of the product lines, and then this is what the program looks like. Obviously, our competitors have their own sizing. They're all very similar as far as the inputs and outputs. I really like the look of ours. It's been redone to match up more with an ISA data sheet as far as what you're putting in the ISA data sheet to be copied over to JVCV. So on the top left here, we can size for globe. We see linear or equal percent. Linear is always going to be when we're doing pressure regulators. Those are always going to be linear type control. I'll touch on linear equal percent later if we have time. Let's see. Let's toggle over to the right here. We got sliding gate versus globe style. I'm going to do a sliding gate example here first. But going here through some of the options. So we have fluids. So we have liquids, gases, and steam applications. So if we have liquids, it defaults to water. But we also have a bunch of different medias that are preloaded in here that will carry over their specific gravity and their viscosity. Obviously, the thicker the media, the more CV you need, the bigger the orifice you need to pass those flows. If we don't have it preloaded in here, a lot of these are just normal glycol, what we use more often, we can hit unlisted fluid. With unlisted fluid, we can type in viscosity, specific gravity of whatever kind of fluid that you're running. Let's see here. One more question here. A question on the pin. The pin should be located for the phone. It should be located in the body of that invite. So take a look at that. Normally you can hit. If you have a unique fluid, you can type it in here and you can save it for future use. So you don't have to keep typing in the same information every time. If we're running a gas, defaults to air, but you can plug in any type of gas, nitrogen, hydrogen, oxygen that you're using. And then finally is steam. And we separate that, the steam and superheated steam, or saturated steam and superheated steam. On the top here, we can put, who is going to be doing the sizing. If the customer is Husky or Thar or BP or whoever, you can put a tag number. So if it's, you're doing multiple of these or for specific location, you can put your tag number in there. If you have another unique line item, you can put that in as well. We can size based on gauge pressure or absolute pressure. Normally we're in gauge pressure. And then this is kind of the inputs that your outside folks and Gilson's apps team and inside team is going to be asking for when we get into applications. It's going to be P1, P2, the temperature, and the flow, and obviously what we know what the media is. So these are kind of the things that we're going to determine what the CV is. So let's plug in 100 psi for the inlets. There's different units over here if you're doing international project or using different units of measure. It's P2. Let's just say we have a pressure regulator. We have 100 psi. Let's set it, a steam application, set it at 50 psi. You can change your temperature to Fahrenheit, Celsius. The flow, let's just punch in 500 pounds per hour. You can also do kilograms per hour. And then it defaults to an 8-inch line size, but we're not going to have an 8-inch line. Let's just do 2. So after we bump this up to a reasonable number. After we put these inputs, we know our line size, we know our inlet outlet flow rate, and what media we have, we're going to hit calculate. I guess I could notice here that with link diameter, so this is the inlet, this 2-inch. If it's an inlet, 2-inch, the valve's a 2-inch, outlet's 2-inch, right? We're going to link those diameters. If you have a 2-inch line necking down to a 1-inch valve up to a 2-inch line, you can do that as well here by unlinking diameters. Schedule pipe, default to schedule 40. We can leave it as that unless you know your schedule pipe, but it doesn't greatly affect the sizing. So after we have our inputs, inlet, outlet, flow rate, line size, and our media here, we hit calculate. And what that does is gives us our results down below. So we were looking at right here is our calculated CV. A calculated CV is 3.07. So what that means is, again, CV is unitless. It's not a square inch, square centimeter number, but it does still equate to an orifice size. So if in Cincinnati, let's go back to my sliding gate here. In Cincinnati, if you say, hey, I want to make a CV with 3.07 orifice in it. Obviously, it's a CV of 50, but if we want to make a 3.07, we could certainly do that. Obviously, it'd just be maybe a lot smaller holes or less orifices. We can do that. So if we would do that and we would put that in line, this regulator or control valve, whatever we're happening to size, would be exactly 100% open to pass 500 pounds per hour with this 50 psi pressure drop. Chris Gilson, I ever addressed that question? Yep, good one. I'll double back here. If the application, if your media is not listed in here, certainly you can input it. But if it is supercritical CO2, for example, if it's a media that changes phases as it goes through, if there's any questions on that, we really want that to be run back through Gilson and then back through our engineering group to get calculated. I know there's certain applications out there where our engineers want to take a second look. So if it's not water, steam, air, nitrogen, hydrogen, standard type medias, if it is a more difficult media, certainly we'll want to take a look at that to make sure it's sized properly. But getting back to the CV here, so the calculated CV we came up with for this application is 3.07, but we don't want to be 100% open when we're flowing. Typically, this is in our notes that I'll be coming up with here in a little bit, but typically on pressure regulators, we're at 30% to 70% travel percent. That's where we want to be. Control valves are a lot more accurate, right? They normally have positioners on them, and those are operated from 10% open to 90% open. So when we're looking back at the sliding gate here, this is our percent of travel, this is our percent of open. So as we see it here, this looks maybe at 30 or 40% open. So in pressure regulators, we like it to be 30% open to 70% open. Control valves, 10% open to 90% open. That is the sweet spot. That is the ideal control range for control. So normally in my head, I always look at the calculated CV, multiply it by 2. to get me, normally in the 50% travel range, plus or minus. So here I'm going to look at what our available CVs are in a 2-inch line. It varies by model, of course. Let me make sure to check one more question here. Back pressure regulator. Yep, Tim, I'll do that as well. So it depends on by model what CVs are available, but in a 2-inch line, this shows all of them. So if I look at the 3 CV, I double it. Our closest available that we manufacture, in bulk, not custom, is a 6.4. This is a linear type relationship. So that's loading. So what that is going to do is it's going to take 3.07. You divide that by 6.4, and that gets you 0.48 or 48% open. So in this application, we have 100 PSI coming in, 100 PSI going out. And if we're flowing 500 pounds per hour all day, this regulator or control valve, whatever we're sizing here, is going to be 48% open all day, right? So that would be your CV selection. When we go to pick our part number, the CV we select will be 6.4. When we're looking at the ordering schematic, this is for any control valve, any pressure regulator, we're going to know our line size typically. You're going to know, hey, this is ductile iron pipe, or we need stainless steel. You're going to know if we need threaded connections or flange connections, right? You're going to know, if you have a spring range on a pressure regulator, we're going to know what we're setting the regulator at. The only unknown really is the CV here. So we have the CV of 6.4, so the pick for that would be pick number 7 for the code, I guess you call it. KV, I should explain, KV is the metric unit. So we're normally looking at CV for the US. So we know most of what we're selecting. CV is always the critical. If we don't do this sizing software program and select our CV and end up with, the max CV in a 2-inch for, let's just say it's 30. If we just put the standard CV in, we're really hindering ourselves in the accuracy of that regulator, the potential accuracy of that regulator, of that control valve. If we put a 30 CV, now we're at 11% open, 11% travel. In a control valve, that's still okay. We certainly would like it to be more towards the center at 50%. But we take 3.27 divided by 30, we're going to get somewhere around 11% of travel. So this is more about optimizing the CV, picking the right one. Obviously, let's just do it the other way. Let's say, okay, we pick a 1.6 CV. We install a 1.6. Go back to this. We install a 1.6 CV in here. We are not here. If we install 1.6 CV, the calculator drops down just a fuzz, but now we're at 185% of travel. Obviously, you can't get over 100% of flow out of an orifice. So this is basically going to pinch off or choke the flow coming out. So instead of having 500 pounds per hour, it's going to be 300 or 400, whatever that number calculation we can do to figure that out. So the flow to that piece of equipment is not going to get there if we undersize a CV. Let's see here. Let me run through one more thing on this before we go to application number 2. So let's do, normally you guys, the customers will have a min, normal, and max, right? So my min flow is this, my normal flow is that. So let's just do an example with that and see how that affects the CV here. Let's do 300 and 700. Let me take a quick look at a couple questions here to make sure I got those covered. Yes, I'll do that. Okay. So if we have 300, 500, 700, right, depending on how many points of use are open or how many, what's being used, if it's a hot season, dry, cold season, we're going to have different flow rates. So now if we hit calculate on these 3 different flow rates, it's going to give us 3 different CVs. Let me go back to my 6.4. So we still have our 3.07 as the normal at 500 pounds per hour. So now you'll see if we flow less, right? If we only have 300 pounds per hour coming through that pipe, our calculated CV is less as well. Obviously, if we're trying to flow more flow through, our CV goes higher. Our orifice size needed goes higher. We're still taking, this is still linear type control, so we're taking these calculated CVs, dividing it by our installed CV to get these travel percents. So we always got to keep an eye on what the range is of these, right? So 30% to 70%. So this could still fit into a nice regulator application. If it starts, these flows start to get too wide, too spread apart, where there's more rangeability needed, that's when we start looking at potential control valves or piloted regulators. If we oversize, I'll go back to Chris Gilson question here. If we start oversizing a valve, whether it be a globe style or sliding gate, especially on the globe style, if you oversize a regulator here, I'll go back to a globe. If we oversize this and we're operating barely off of the seat, the plug is going to just beat itself to death, right? Because it's going to go open, close, open, close, open, close, just trying to modulate it 3%, 5%. 10% open. So it's going to wear, the valve's going to wear out prematurely versus operating all well off the seat in that 30 to 70% control range. So you'll get premature wear if we oversize a valve and the valve just beats itself to death. I do one more thing to cover back over here. So we have our, if this is our application, 100 down to, we're controlling it down to 50 PSI with these flow rates. The travel percents look great. What we're going to do is we're going to come up to the top, and normally Gilson will supply this with you, to you, the apps team or the outside team. This is, looks like an ISA data sheet, and this is what you guys will be presented. It'll tell you what your tag number was, or who's, your customer or whoever's, whatever it's for. It'll show your inputs, 100 PSI down to 50. It'll show your different flow rates, pipe size. Here's your calculated CV that we saw, the selected CV. This is your installed CV. This is the CV we're going to put in those in the sliding gate or in the plug orifice combination. And your travel percents. This will also, another big point of this is your predicted noise. We don't alarm it unless it goes above 70 decibels. Sometimes when you get really high pressure drops with larger flows, this will tell you if you're at 85 decibels, 90 decibels, whatever the program comes out and says. So those are the times maybe you need to do a dual stage regulator, take 500 down to 300, then 300 down to 100 if it becomes too noisy, or you jacket the valve, or if you put it somewhere, if it's somewhere where it's noisy anyways, it doesn't. I just want to point that out. The predicted noise is there. Here's the sizing recommendations. This is industry size, industry wide. This isn't what we recommend. This is kind of across the industry for pressure regulating valves, pressure reducing valves. We size 30% to 70% on the max end. Back pressure regulators. They kind of act more like a relief valve. We don't call them relief valves, but they relieve excess pressure in the line. We only like sizing those to 50%. We go over that, you run into potential issues if something upstream fails, breaks, and we exceed the capacity of that. So 50% on back pressure regulators. Diaphragm control valves. These are the ones where you have positioners on 4 to 20 coming from the PLC. Extremely accurate. So those can operate 10% to 90%. Motor operated valves, same type of thing with an electric actuator, 10% to 90. Temperature control valves. So this is the Mark 80, what we have, which has a capillary and a bulb that would go into a tank for heating purposes normally. Extremely accurate, 10% to 90. And then our piloted regulators, extremely accurate as well, can go to 90%. So that tidbits on the bottom of every data sheet. We size per ISA 75, which is the industry standard for sizing. So it's all the calculations are per their standard. So you can save that, print that to a PDF, whatever you want to do. But that is That's what happens when the flows change. I'll go through one more application here. I'll make sure I got all these things answered here. All right, let's go. Punch in application number 2, and I'm going to change one more parameter and show you another change that'll happen. So we've changed flow, but now we're going to change DP. So we'll leave this one as a globe style. We'll size this one for water. It doesn't matter. Run some numbers. Let's do 100 psi of water. 50 psi is your P2. Let's say it's ambient water. And let's do 50 GPMs. I'm going to leave this gallons per minute, but you'll see the other units, right? I didn't show that last time, but you'll see the other units that are available for that. And let's jump this down to a normal line size. 1 to 1 inch and a half, maybe. So it looks like a 1 inch line for this. All right. So here's the application. We have 100 psi of water down to 50 psi of water, ambient, flowing 50 GPMs. Come up with a 1 inch line. Our calculated CVs at 7. I put it installed CV. This is what's going into the control valve, into the regulator at 11.5. My travel percent's at 61. All is good if we would go with that. But let's just say we've changed flow before. We know what that does. More flow is higher CV, low flow is lesser CV. But let's adjust P2. Let's just say we go down, now P2, we underestimated or overestimated it. It's at 30 psi. Notice that what that does to our CV, it lowers it. It lowers the required CV. The more differential pressure you have in the line, the easier it is for media to get through an orifice, to get through the sliding gate or get through the globe style design, right? So our CV goes down, meaning our installed CV could go down. And obviously, if the CV is going down, you can also talk yourself potentially into a smaller line size. Maybe 1 inch now goes down to a 3/4 inch. Conversely, if we take this pressure up, let's say now it's at 70 psi. Now we have a smaller differential, and the CV goes up, right? Less differential. It's harder to flow media through an orifice. So now we're getting in. If we left this at the 11.5, and our differential is only 30 psi now, same flow. Now we're at 79% travel with the nine calculated CV. So we're out of that maybe regulator range, maybe talking control valve range, or we go up a line size. So changing P2 is very critical, or knowing P2 is very critical. If you're obviously emptying into a tank or a recirculation line, it's going to be atmospheric pressure. We know that's going to be 0. If there's elbows and T's in the line, maybe that adds a few psi. But knowing P2 is very critical. You can kind of see what the change does here. Let me get this thing to potentially cavitate. This program also gives you warnings on cavitation. Nope, it's not going to cavitate. Let's see. So if I go down to 5, it should cavitate. There it is. So now I'm taking water from 100 psi down to 5 psi. Huge pressure drop for water applications. This is going to tell you it's going to cavitate. So it'll tell you a few different warnings if something isn't going to work like it should or isn't going to function like it should. Cavitation, obviously, you look for maybe an additional step down, taking 100 down to 50, then 50 down to 5. So there is flow warnings that are listed there. Let me check one more notes here. Yeah, covered that. I'll double back to Chris' question. All right, Chris had a question about the orifice. Oh, I gotta get out of that. Had a question about the oversizing of the valve here. What that does, other than beat the valve up and we oversize it, right? We're at 5% control range. Other than beating itself up and not lasting as long, we also get more erratic control. Meaning, if we're trying to hold 50 GPMs downstream or 50 PSI, whatever trying to control, that reading is going to fluctuate more than if we properly size the valve. So if we're reading 50 PSI and this valve's oversized, not trying to operate at 5% open, it's going to fluctuate 48 to 52 back to, not holding tight at what the desired reading is supposed to be. So it just doesn't operate well right off of the seat, and then when it's basically full open, over 90%. So good note there, Chris. Let me get back to, so that is the sizing program. So these are the common things we need to input, P1s and P2s. And then obviously when we're putting our min, normal, and max, we always got to make sure we're looking at the CVs that we're given and the percents of travel that we're seeing. And then, like you said, up here, you can hit report and hit that to a PDF. The first time, I believe you have to allow a pop-up blocker, but otherwise you'll be able to print that to a PDF. So let's go back to, make sure I touch on all this. The positioner, yes, I think Chris asks, is the positioner will hunt as well. I think it will, but it's also being, I think the plug is being pulled in the open and closed position a little bit as well, so that is hindering it. I think when I think of hunting, I think of more of hysteresis in the linkage and the connections. But yes, I think it's just overall recommended not to control at under 10 PSI or under 10% open or over 90% open. I just want to go in through, just close this up here. What we're looking here is the Mark 60. I assume most of you have some of these in your plants. I wanted to show the red domes so you can recognize it potentially. And then this is the interior cutout. So this is I want to finish this up by just discussing very quickly control valves versus regulators, right? Obviously CV is tied into both of them, right? So the sizing program we just did sizes control valves, sizes regulators. It doesn't discriminate between the two. It's more of what is your percent travels, what is the accuracy needed for the application, is feedback needed for the application, kind of dictates control valves versus regulators, but the sizing program calculates CV for both. When we install pressure regulators in the line, as we see here, these are threaded into line, or you have 150 or 300 pound flange in the line, and these are set it and forget it, right? So this is threaded, flange in the line. Joe comes up here, he cranks this adjusting screw down, compresses the spring. You're gonna have downstream piping in your gauge, right? The gauge is sitting, could be attached to the regulator, or typically it's downstream. And if we want that set to 50 PSI under flowing conditions, it'll go crank this down, wait till he sees 50 PSI and walk away. And it'll run for 20, 30, 40 years untouched, right? Because it's sensing the pressure underneath the diaphragm, and it's auto adjusting. Right? You have flow and pressure coming in, but it's auto adjusting to keep this downstream pressure gauge held to 50 PSI or whatever the desired set pressure is. But with regulators comes this inherent property called droop or offset. So as flow increases and decreases, let me get my mouse back here, as flow increases and decreases, the regulated pressure changes as well. As you open up for, this is more for inside your head, as you open up more faucets in your house, the pressure drops, right? Because one faucet uses 10 GPM, another faucet uses another 10 GPM, right? So as you increase flow, pressure drops. So if we have this application set at 40 PSI, we start opening 10 GPM, 10 GPM, 10 GPM. Now we're only at 30 PSI, 35 PSI. So that is an inherent property that exists with pressure regulators. So there is some pressure loss in the line if pressures are changing, or if flows, are changing. If we look at control valves, on the other hand, right, pressure regulators, set it and forget it. There's no 4 to 20, no PLC, no anything that connects to it. If we look at the control loop, we get into control valves, we have pressure transmitters, right, or flow meters, or level devices that are measuring whatever we want to control. you have your PLC, your DVC, and then you have your positioner, you have your control valve here that's adjusting and trying to keep the measurement device happy or in balance. And the control valve will overtake and do whatever it needs to do to make sure this holds tight at 40 psi or 50 GPM or whatever we're trying to measure. So control valves, extremely accurate. Regulators, lesser so, but there's obviously a cost difference between a regulator, one piece of equipment, and control valves, PLCs, pressure transmitters, and everything that goes in between. Obviously, if feedback's needed, if it's a critical process, control valves may be desired. Some applications, if we're just taking 100 psi of nitrogen and want to regulate it to 30 psi, regulators may be more costly and economical, an advantage there. So I want to make sure I pointed that out. So you have control valves versus regulators, the cost difference that goes between them. But just knowing if in regards to sizing, if our flows start to get so far apart where we're in that 10% to 90%, we're looking at control valves, something that regulators probably cannot control too. So it kind of depends on the difference in pressure, certainly, and then the difference in flows. Let's see here. What else? Let me cover a couple other questions here. Oh. All right. I think I got most of the questions answered here. Ann asked, are there any special considerations for sizing when the application is pulses of flow? Is there any special considerations for sizing when the application is pulses of flow? It's a good question. I'll have to get back to you on that. I don't want to throw a guess at that one. So I will get back to you, Ann, on that. I don't know the exact answer for that one. Let me check a couple other ones here. All right. All right. I appreciate everybody's time. If there's any specific questions, certainly can add them to this chat, and we'll get back to you. I am your sales contact to get back to you. And if there's anything additional you guys would want as individual companies, more in depth on certain things, we're more than happy to do that as well. Again, appreciate everybody's time. Again, have a great day. And if there's anything else you need, please let us know.